Okay. Thank you, everybody, once again for joining us. We're really appreciative of your support so far. We're grateful. I'm Bilikiso Olatunji. I'm the founder and co-organizer of the Our Ladies Abuja, Nigeria. So we're grateful for all those who are joining us all over the world. Thank you so much. And my special gratitude goes to our local participants as well. Thank you all for joining us. So I would not take too much of our time. We've waited and we've given the 5 minutes grace for others to join. We hope they will join soon. So I wouldn't take much of our time. So I'll go ahead to introduce the topic for our workshop today. That is from complex to clear, okay? Understanding your NLP model. So we're going to be talking about explainable model, machine learning models here today. And the most capable person that we're having today is Cosima Meyer. So she is a data scientist she's working with IBM. So where she aims to make machine learning explainable. Okay. As the founder of Our Ladies College, I hope I pronounced that well, and an active member of Pi Ladies, she strives to bring the two communities together. And let me just bring this up. Okay. She's also now one of the executives of the Our Ladies Global. So we're really honored to have you here. So going forward, during our PhD studies at the University of Mannheim, good. Okay, Cosima discovered a passion for sharing knowledge, both by writing technical blog posts and by developing open source software. So you're welcome today into our midst, Cosima, and we're really grateful to have you. So I would like you to take the floor, and I think you can do more justice to introducing yourself better. Thank you so much. I'm grateful. Thank you.
Thank you so much for the lovely introduction. I couldn't actually have done it better myself. So that was amazing. And thanks everyone for joining today and for having interest in the topic. Let me quickly try sharing the screen so that we can get started. Amazing, it works. Cool. Okay, so what you should be seeing right now is again the cover slide, right?
Yeah.
Okay, perfect. Before we get started, I'll quickly try to share something with you in the chat. It's a link that goes to this GitHub repository. So in case you want to look up the slides, in case you want to look up the Google Colab, the notebook that we'll be working with later, it's all covered here. And there are also a couple of other resources in case you want to read up on stuff later that we can't cover in that much detail during the session today. So it's all collected here. But let's go back to the presentation. So without kind of any further ado, let's jump right into from complex to clear and to kind of tell you how to understand your NLP models. And just before we get started with that one, quick motivation why I think it's so important. In my work, I work both with structured data and unstructured data. Unstructured data is typically something like text data, video data, audio data, something like that. And when working with these type of data, the models become increasingly complex. And by becoming increasingly complex, it's also increasingly difficult to understand them. And they are often kind of labeled as black box models because things go in, things go out, and people are happy or they are not. And I think understanding what the model actually does is one of the core parts that every data scientist should know about when training the model, when evaluating the model, not only for the training and improving purposes that you have when doing the model training, but also when it comes to understanding whether the model is fair, whether the model is biased, whether there are any things that are a bit off with your model that you're not aware of once you're training the model, right? So this is why I think it's really important to understand your models better. And I'll show you in a second how I'm doing that and one way of how you can approach this kind of challenge. Before that, just I mean, Vicky, so you said it so nicely. So I'm working as a senior data scientist at IBM. I also co-lead the data science and methods community there. I'm a member of the Our Ladies Global team, which means I'm there supporting the full Our Ladies Global team, which is like more than 20 people actually, by maintaining and developing the website and pipelines in the background. I think someone is not on mute, which makes some kind of echo in the back. So I'm not sure if you could unmute. Thank you. Awesome. That's cool. So I'm supporting the Our Ladies Global team. And I also co-founded Our Ladies Cologne, which kind of brought me right into the world of R, which I really enjoy because it's such a nice and lovely community. And I'm also one of Google's Women Tech Makers ambassadors, which aims to make the community, the coding community, a bit more diverse, a bit more kind of colorful in a way. And this is also what brings you the slide theme here, because this year's International Women's Day at Google's Women Tech Makers Ambassadors stands under the topic of impacting the future. And I think by clearly putting the focus on making these models understandable, we can definitely impact the future. Not only in light of the recent developments that you have with the GPT and all these things, but also when it comes to something that was recently established in the EU, it's the EU AI Act, which kind of pushes things in a specific direction, where we need to make sure that we understand what the models are doing. So with having that said, we can dive right into what we're doing today. And if you have any questions, I try to monitor the chat. If I miss something, really key, so I'm happy if you jump in and raise it so that awesome, cool. Because I think it's really nice if we have this as interactive as possible. So again, like use the chat and I try to keep track of what's going on there. Cool. So let's talk about NLP models. And for this part here, we'll be talking specifically about BERT. BERT is a specific type of how you can kind of build your model. It's called bidirectional encoder representation from transformers. So it's an acronym, but and BERT was it's one of these popular models that is out there. It was released already in 2018. You can do a couple of things with that, for instance, like sentiment detection or classification. You can do like standard classification by kind of classifying, for instance, emails into spam or not spam, something like that, for instance. But you can also do like some kind of question answering things. So it's really powerful. And we're using this one, and I'll show you how to access it and how to use it for the use case that we have here. So, but first, let's kind of take a step back and try to better understand what a foundation model is, because that's what BERT falls into. I'm pretty sure you've heard all the buzz around foundation models and large language models, but I just wanted to make sure that everyone is on board here. So foundations models are typically are pre-trained models, which means they were trained on a really large corpus of data. It could be, for instance, Wikipedia or some kind of newspaper articles or something like that. And you can think of that like they were learning kind of the world, they were taking in the world knowledge and learning a specific language. And then you can use this model and, for instance, fine-tune it and make it even better on a specific topic. So this is what the pre-trained stands for. And they are also generalizable and adaptable, which is really cool because they're not trained for one single purpose. As I said before, BERT can be used for instance, sentiment, it can be used for classification, it can be used for multiple things. So it's really, it's adaptable. You can use it for multiple things, which makes it a really nice thing to have. And within these foundation models, they don't only consider like text data, but they can also be there for like some kind of image data, some kind of audio data, some kind of these. So within these foundation models, what falls under this is what we know as large language models. The abbreviation is LLM, and one of them again is BERT, but it's also GPT-4, which again most of you will know within the chat environment of ChatGPT. So this is kind of the background, and let's dive deeper into what a LLM is. Again, as I said, it's usually trained on a really large corpus of data. Typically, these corpuses consisted of like something that can be easily crawled using the web. For instance, Wikipedia might be a good resource because Wikipedia has the word knowledge, it has the way people write in different languages. So it's often an easy starting point to train your model. And then you end up having, like, once you have this kind of data and you trained your model, you end up having the pre-trained LLM. And I think, I'm sorry, again, I don't see the participants, but I think there's again someone on unmute. It would be really nice if you could mute yourself because I get lots of echoes in the background. I'm not sure if the others are hearing that as well. So you end up having the LLM, which can be pre-trained, meaning just by the corpus, or you can use additional labeled data to fine-tune the model. And one thing could be, for instance, so one way of thinking about that, this whole fine-tuning process, because it's one of these buzz terms that people are using and probably not all are aware of what it actually means, is so you have the model, it knows the language, and you can think of the model as a student. So the student learned the English language because he was taught the language by his parents or her parents. And then he went or she went to school and learned other things, improved a bit the language, but the student doesn't have any clue about biology. And this is what we mean with fine-tuning. So then the student learns biology, specific terms of biology, specific patterns in biology. And this is like giving the model new data to fine-tune the model on a specific topical area that the model is not an expert in. So you end up having either of them. And there's often no need to really fine-tune things, as we'll see with the notebook that I've prepared, because some models are already specifically tailored to specific use cases on top of being a general model. So you have your LLM, and then your LLM can do multiple things. I just put a few down here to give you some kind of inspiration and probably a better understanding of what this large language model can do. But again, it's not exhaustive. There's so much more to that. So for instance, we can have some kind of sentiment analysis. We're giving the model some kind of text snippets, and the model classifies it as being positive, negative, neutral, whatever categories the model was trained on. Or it could be also named entity recognition. That's something that is really typical and a typical use case in NLP, where you want the model to classify March 15th, 2024 as being a date. And for instance, London as being a place or a city. So you want to name the entities that are in the text and extract them. Or you could have also a customized classification. Again, as I said before, for instance, you have a bunch of emails and you want to make sure that you classify spam versus non-spam or info emails, some kind of mailing list correctly. So you have some customized classification for your emails. But it could also be some kind of Q&A where you provide the model with a question and then it returns an answer. And that's what you typically know from ChatGPT when you're using that. So this is kind of the overall intuition of what foundation models are and what a LLM is. And again, if you have any questions, feel free to put them in the chat. I'm happy to answer them as I go along. So when we dive deeper into the BERT part, or the BERT models, and to get an even better understanding of how these models are structured, and I think it's essential to really understand these models, let's take a quick look at how the model is pre-trained. So how does this whole pre-training process work? And it works actually in 2 steps for BERT in particular. So that's what I'm referring to here. So you have, in the first step, you have something that's called masked language modeling. And what you have here is you have the bottom part. It says here, Mannheim is a beautiful city. Mannheim is a city, and you're masking one word. So it's kind of like a text where you hide a word. And then the model learns, okay, here goes beautiful. So it knows Mannheim, that's the city where I'm living in. And I should probably explain that as well. Mannheim is not known for being the most beautiful city in Germany. It's actually known for being one of the more ugly cities. But I think the beauty comes from within. And I believe Mannheim is a beautiful city. That's why I brought up this example here. But so you're masking one word in the text at a time, and the model learns to predict which word should be here. And it is able to do so because it gets a ton of training data. So by having just having 10 examples or so wouldn't be enough, but by having hundreds of examples, it really helps, and it really lets the model learn these things. There's a question in the chat what CLS means, and what probably also SEP, it's similar to that one, what it means. These are terms that are used here to classify whether it's the beginning of a sentence, whether there is some kind of a separator. The separator would be a dot, for instance, or a comma, to let the model know the sentence starts here. Here's some kind of separator. So it's what you do typically in NLP. You break down a sentence into subcomponents. These subcomponents are called tokens, and this is a specific term that is used within the transformer architecture to let the model know what the beginning of the sentence is and what a separator here is. So excellent question. That's cool. Yeah. So you're masking one word at a time, and the model is learning which word should be there. And then in the next step, so we have this masking one word at a time, the model is learning which word comes, and then there is a next step that it learns, where it learns which kind of next sentence should come. And here we have, again, the example with Mannheim. Mannheim is a beautiful city. And then which kind of sentence should go next? Should it be I'm working as a data scientist? Probably not. But it should be something like it's close to 2 rivers and quite green, or something like this, something that is close to describing a city. And because the model has the true data, it has all this training data, it can compare the prediction. So whether this sentence B here, it's close to 2 rivers and quite green, really matches what, if it really matches what the model originally was given. So if it's really true, so to say. So these 2 things, and it's actually quite, from this abstract point of view, quite simple kind of. It's also, it kind of mimics how a human being learns a text, or learns how to speak, how to write, a logical consequence, which makes it really nice and intuitive to understand how these models are trained. Of course, it gets more complex once you look under the hood, but looking at it from this perspective, I think it kind of gives a nice gist to it. I think there was another question. What about small and rare cases? How does the model adjust to those cases? Well, that really depends, and that's, I think, why the explainability is so important. And it also it's also about I think there's, sorry. Okay, there was not someone saying something. Okay, I thought there was another question. Yeah, that's an excellent idea. Billy Kiesel, is it possible to mute all participants or to force mute or something like that? I think that
Yes,
makes,
exactly. That's what I want to do now. Let me
okay, cool. Amazing.
come in.
Amazing. Awesome. So I think there was this idea, there was the question about small and rare cases, how the model adjusts to those cases. That's an excellent question. I think that's where it really helps um, to have the explainability part in there as well, because most often for these like rare cases, you're not really aware that they exist. So for instance, I think it was Google Translate or some kind of translation machine, where people discovered that when there were like more like how do you say that, like professions that are more likely to be associated with male people, when people wanted to translate that one and they were using some kind of gender neutral term, which is something that happens in the Turkish language, for instance, because I remember the example was in Turkish, it was more likely that those cases were translated for the woman, for the male. So, for instance, there was a sentence saying like, "She is a nurse and he is a doctor," but the pronoun he and she in Turkish, it's gender neutral, so it could be either or. It could be she is a doctor, he is a nurse, or he is a doctor and she's a nurse. And what the translation machine actually did is it translated it into she is a nurse, because nurse was more likely to be associated with a female pronoun, and he is a doctor, and Dada is a doctor was translated as he's a doctor because doctor was more likely to be associated with a male pronoun. And it might be a rare case that a male people is a nurse and vice versa. So the model was learning to associate these things with the specific gender. And by having some kind of explainability in the background as well, you can detect these cases. So you can then either, for instance, during the fine-tuning phase, like retrain kind of the model, or to add more examples into the training data, or also follow other approaches just to take care of that. But that's what typically a data scientist would discover, and where the person would also find a solution for. But it's really a nice bridge to bring us back to why explainable AI is so important to also understand what the model is doing. I hope that helped to answer the question. Okay, so what we learned now is how your model is trained. You have the masking part and you have the next sentence prediction. Again, kind of as a human being would also probably learn a language and context and these things. And then in the next stage, it's also important, and that's something that we raised a bit earlier as well. Next slide. We need to understand how BERT captures text. And that's something that you see here. So you have the text, Mannheim is a beautiful city, again with the CLS and the separator. And then we have different levels of embeddings. And the embeddings are at the first line here, you see the token embedding, meaning like each word is separated, or the sentence is separated into separate tokens. And they are like kind of like follow a sequence here. And then you have the segment embedding. And the segment embedding would be, you see like here, the lower index A's down here, or subscript A's, sorry. That would be something like a sentence, for instance. If we had a separate sentence here, it would be EA and then followed by EB, so that the model learns, hey, this is a new sentence, but it still belongs to the sentence that you had before. And then we also have the positional embedding, where each token gets its own position because it matters. Whether, for instance, sometimes the place comes first or last, depending on the language that you're learning, or where to put the adverb. Does it follow right after the verb, or is it at the very end because it says something totally different? So this is why the positional embedding is so important. And by this, we try to teach the model to learn as much of the language as possible in an automated way or in an automated fashion. With that, I would switch to the notebook, and you can access it using the link, and I'll put the link in the chat in a second once I copied it, so that you can also access the notebook. You'll have, oh wait, where is it? Here. You'll have it in a sandbox mode. I have it here in a non-sandbox mode, but it's basically the same. Let's see if it still works, because it was disconnected. Perfect, awesome. Because once you run it, you'll have to install Python and R, and we'll be working with both throughout this tutorial today. Because, I mean, that's how I was working when I was doing my PhD. I was taking from both worlds, whatever works best. And I think it's really nice to combine those two. And what we have here, it's called a Jupyter Notebook, where you can work with both Python and R in it, similar to R Markdown or Quarto. And what I was saying is it can take some time, in particular for the steps to install the R parts to run through. So don't worry about that. You can either follow in the sandbox yourself, or you can just follow on the screen what I'm doing and use the sandbox at a later stage if it takes too long to run the R parts in the beginning, and get back to them to try yourself what we're doing here. So before we get started with the notebook, a quick disclaimer. It is based on a blog post that I co-wrote with Andreas Küpfer, and you have the link to the blog post here as well. It's like tons of other material in there that I couldn't capture within the scope of this session here, but which I think could be interesting for you. It also has a couple of links in the beginning. So if NLP is something totally new to you, feel free to go to this blog post. It's purely R, and it gives you like a good understanding, I hope at least, of all the basic concepts that you can use in NLP. If you're new to BERT, within the blog post, there's an introduction to BERT, and that you can reread to get a recap of what I just talked about. And then in the blog post, if you're just aiming for explainable AI, also outside of NLP, there's also a section on that one specifically. So I hope this serves everyone's interest. Yeah, so with that being said, let's jump into what the notebook has to offer. So as I said, first we're installing a few libraries, some in Python and some in R. And basically, if you don't know Python, it kind of works in a similar way as R when it comes to the logic. So here we have the pip install, which is something like install.packages, and we load the libraries like library parentheses open, library name, library parentheses closed. And that's what we're doing here with the import statements. So it's nothing kind of like super different than the steps that we're doing in R. To use R within the Jupyter Notebook, you have to install rpy2. That is something that we're calling here with the loadxt rpy2 IPython. And then you can use code chunks similar to Quarto or Markdown. They just have to start with the %, R, and then it's an R environment where you can like do whatever you please, and also use the output of the previous Python chunks within a new chunk, but you'll see it in a second how that works. So that's kind of the logistics here. Then I wrote down like all the things that I just explained for you to read up, how a BERT model is being trained, how a BERT model works, and how it captures text. And this leads us to where we want to start. So what we're using the Transformers library. And the Transformers library, if I quickly jump here, comes from Hugging Face. And Hugging Face is a really nice site, I think. I mean, probably you know about it. If you haven't, it's the perfect starting point for you to find models, find tutorials, and also kind of find the framework for using those models. So people basically, they train models, upload them into the hub, where you can access the models then from. And there are multiple models that are open source, that have typically a model card that describes what the model is trained on. You kind of get the credentials from the people who trained the models, which is all very important. And you can easily access the models using the Transformers API, meaning using the Transformers package, to run that within your environment. And that's what we're doing here. So I looked up a model that I wanted to use with you. It's the distill bird here in this part here. That's where bird is in. And we use distill bird, which is already fine-tuned on sentiment analysis. And it's fine-tuned for the English language, because I wanted us to focus on the explainable part. And what you do is in Python, unlike R, you use the equation sign instead of the arrow to assign something to something. So we're assigning the name to model name. We call the tokenizer, which is the thing that splits up your sentences into the separate parts. And we call it from the model. So the model always comes, or when you access the model, it always comes with a pre-trained tokenizer on a specific on a specific case. Here, the English language fine-tuned for sentiment, but it could be also a model trained on German data, trained on French data, whatsoever. So it comes with the tokenizer, and it also comes with the model. So these are the two components that you get, and that's what we are accessing here. We have the tokenizer and we have the model, and the Transformers API knows which tokenizers we want by passing the model name here. And I mean, probably you would ask, like, why are you not using R for this one? As far as I know, there was an approach in R to develop the package RBird. I also put it up here in the very beginning, but it has been discontinued. And now there is active development, but it's still experimental. It's called Torch Transformers. It uses Torch as an underlying framework. RBird uses TensorFlow. These are the two approaches how you can do it. So there's Torch Transformers, because Torch apparently works, or PyTorch works better within the R environment, but it's still very experimental. So again, as I said, also during my PhD, I picked parts from the programming world where it worked best. And I think here Python has, at the moment, a clear advantage, because you already have this kind of framework being set up. So that's why we are using, in particular here, Python to access the model and to train the model, or to predict the statements in a later case, to classify the statements in a later case. But that's just as a background. Okay, so what we have is just for you to understand, and to understand how this encoding, the tokenization and everything works. What we have is, we have the sentence here that you've seen before, like the sentences, actually it's two. It's Mannheim is a beautiful city, and it's close to two rivers, and it's quite green. What we're doing is, we're taking the sample and we're storing it within sample. Let me quickly show you how it looks like. So that's what you get. It's all lowercase, but it's still the sentence in a human readable way. In the next step, what we're doing, we're encoding the sentence. And to get the output in a, again, human readable way, we need to convert it to, like we need to wrap this thing here around. But once you run that, you will see you get these like kind of fancy tokens that you've seen before with the CLS and the SEP. The SEP here, which is at the end. And this is for the human to be able to read it. But what you need to know is that what the model is actually doing, it's converting, or the encoding itself, it's not looking that nicely. It's actually numbers. So we have a vector representation of words within as numbers. So what the model is, or what the tokenizer is doing, it converts sentences into numbers, and numbers are things that the model can work on. And this part here is important, and you'll see at a later stage why. Okay, so with that, we can now continue and apply BERT, the model that we just loaded, to a data set that I picked for you. And the data set comes from Kaggle, and it's called Yelp labeled CSV. It's also in the GitHub repo. We're accessing it here directly from the GitHub repo. I'm doing that now in Python, but you also have the very same code here in R, so that you can redo it also in R. So the data is Yelp data. Yelp, if you don't know it, it's a platform where people can recommend, for instance, restaurants or hair salons or whatsoever, and they can write a critique. And this critique can be either positive or negative. And what we're getting is, we quickly load the data. It's similar to the approach that you would follow in R. You read in a CSV, that's what's happening here. And you can then look at the data. And I picked here the tail because it nice, or the tail means the end of the data frame, because it nicely shows that it's a bit messy. I mean, as always, data is a bit messy. I don't want to spend too much time on that here. I just wanted to show you what the data looks like. So we have 6 columns. In the first column is a bit of text, and some of the next columns is a bit of text as well. And then we have one column that looks like a bit weird, where we have zeros, and there are actually also ones in there. This is the column for the sentiment. 0, I think 0 is negative and 1 is positive. And we want to have that in a nice way. So we want to have one column with the text, one column with the sentiment, to know what the true sentiment is, to compare what the model is actually predicting, right? So what we're doing in the next step is we're like, and that's a really Pythonic way of doing things. You define your own functions. Python is a lot about defining your own functions. So we concatenate the cells, means we're bringing them together, and we also get the label. So if the cell contains 0, 1, or as a string, 0 or 1, it is returned being positive or negative. If it's not in there, if the cell doesn't have this, we return nothing, kind of. And we quickly run that, and then you get something that is a bit more beautiful. Here in the beginning, the first 6 columns are still the nasty, not so nice columns with the messy data. And here, and that's the important part, are the columns that you have for the full text, where the text is like nicely concatenated, and we have the sentiment in a human readable way. But that's, again, there is also code in R for that if you prefer R here. But that's all I wanted to show you here, to let you know how you can work with that data, because once you take a look at it, it will look like, it just looks messy and you need to clean it up before. If we now focus on those 2 columns that we're really interested in, we stay with the sentiment, with the true sentiment, which I called sentiment actual, and the full text. And what we want to do now is we want to see how good BERT is doing in classifying those texts. So what we have here, for instance, is something like, whoa, love this place, which is clearly positive. And we want to know whether BERT also classifies those things as being positive. Bird has never seen these examples, ideally. And we want to see how good it is in classifying them here. So what I gave you here is, again, a lot of text for you to read up things to better understand what is going on under the hood. But what we have here is we have the full sequence of steps you would do to call bird and predict the sentiment. So again, we have the same code chunk as above. We have the model name, we call the model, we call the tokenizer, and this again, as I said before, and that was kind of the cautious word here, it's really Pythonic. You define your own function. And this function here is called predict sentiments. And it takes the tokenizer, takes the sentence, and it returns the, like it kind of tokenizes your sentences, and then it does the prediction and it saves the output that we get from these predictions. And then we get, because each of the model kind of gives a, if you want a probability, how likely is it that it's positive, how likely is it that it's negative, how likely is it that it's neutral. And in the next step, we get this class that has the highest probability. So if the model thinks it's positive, positive has the highest probability, here it will return being positive. And that's what we basically return down here in the last step. It looks like a lot of code, I know, but that's kind of the logic that is happening in the back. So we call this function, nothing happens. That's we just defined it. It's like writing a function in R. And then we do something that is happening here. We predict the sentiment for the full text. So what this thing here is doing is we have the data frame, we have the column full text, and we apply to this very column the predict sentiment function that we just have written before. And again, also very Pythonic way of doing things. You write an anonymous function called lambda function here. It's basically something that you write when you don't want to specifically write a new function. So then you call lambda, just that you know, but you don't have to care too much about that here. So that's what we're doing. We quickly run it, takes a bit, because I think the data has something like 900-ish entries or something like that. It's fast, but not super fast. And once we're there, and once it's done, we can have a look at it. And what you will see is you'll then have a new data frame where you have the sentiment actual, the full text, and also what we define here, the sentiment predicted, basically what the model thinks what it should be. Let's give it some time to finish. I should have kicked that in a bit earlier and then before going into the major talking, but I wanted to show you how it really looks like. And this is also something that like with the Jupyter Notebook here in Google Colab, it's done. You can also upgrade the computational power and everything. But if you're running that on your local machine, what we're using is the Stillbird. It's a really like condensed model that runs faster, but still has a like similar performance in comparison to the full bird, if you want to call it like that. But that's something that you have to keep in mind once you're running these things on your local machine. It might take some time. It's not like it's not like really quick, but it's rather like it can be a slow process. So now let's look at the data. And as I said, what we have is we have the true sentiment, we have the full text, and we have what the model has predicted. And so far, what we can see is in Python, the head function gives you the first 5 entries. What we can see is you have the model performs really well. It just has the sentiments correctly predicted, at least for the first 5. But that's where, like in the end, understanding your model also comes in. If there are any questions, feel free to ask them. Again, like put them in the chat. I try to monitor the chat and take care to pick them up. So we're applying BERT, because if not, we'll move on to understanding your model. I think there's a question on the recording. I think that will go up at a later stage, but I'm sure, like, because we're recording, there will be one. If there are no other questions, I'm moving on to understanding your model. And what we have here is we have 3 different components to understanding your model. And there may be more, but those are the 3 like kind of out of the box components that I typically use to get an idea of what the model is doing. And we'll cover all 3 of them and go back and forth with the notebook to see how to apply them directly hands-on with the model that we've just applied to the data. And what you probably also recognize, I mean, I said it before, but we didn't fine-tune the model, right? So we just used the model that is out there and applied it to our data. So there's no, like for our case, there was no need to provide additional training data and additional test data. We could have done that as well to even improve it a bit further. But what you will see, it's quite nice, just out of the box already. Let's jump in first into the standard model metrics. And this here is kind of the depiction of it. And there's, of course, more to it. So you can also dive deeper into them. But standard model metrics, what I mean with that is, first, what I like to look at is the confusion matrix, because it kind of gives me a disaggregated view of where the model is right and where it's wrong. And for those of you who don't know what a confusion matrix is, it's the thing that we see on the left-hand side. Here you kind of contrast those things that were actually positive sentiment with the model where it says, here, this is really the positive sentiment, and also depict those where the model thought it might be negative. And it does the same for the actual negatives. So with this, you really get a nice view of in which categories the model is off and to which percentage. For these, like, I mean, 2 classes that we have here, it's probably a nice thing to look at, but it's not super insightful. But once you're working with more complex, or like with models that have more classes, like 20, 30, 40, something like that, I feel, or my experience is that a confusion matrix really is a nice point of getting started, because it kind of builds the backbone of many of those other standard model metrics that, you know, for instance, like the F1 score or recall and accuracy, precision, and all these things. I also like to look at them, but they give you more, like, those are kind of, if you want to, like, if you don't know what that is, we'll not go too much into detail for them right now and here, because they don't tell you that much about what the model is actually doing at which specific case. They are more giving you like some kind of quality metrics, how good your model is performing, and they are based on the confusion matrix in a way that they kind of, or not kind of, but they use the information that the confusion matrix is giving you and recalculate comparable metrics that you can then use to compare multiple models. So if you want to compare multiple models, it's good to look at these, or it's always, I mean, it's not only if you're comparing multiple models, but it's always good to have these and to look at them, but they are in particular good if you want to compare multiple models on a higher aggregated level. But if you really want to go into what the model is doing, I think other approaches are more valuable. But that's what the standard model metrics are about, and we'll dive into them now to see how to apply them. And what we're doing here is we're calculating the confusion matrix using the scikit-learn package, which is a typical Python package. And we're defining the categories, it's negative and positive. We're using custom colors, and we're also plotting it so that you get this nice confusion matrix that you see here in there. And that's what we're doing here. And then it looks like this. So what you see is those are the negatives. That's the prediction, what the model says. And you also see the positives, and you see where they overlap. You can also, with the scikit-learn package, but there are also Python packages, R packages, sorry, for that. You can also get a classification report, which you see here, which gives you like tons of values to compare. And again, they're a really nice starting point to compare multiple models. But from what my experience tells me, going really into the data really helps to also improve the models. So at a subsequent stage, it's really important to not only look at the numbers here. And what I promised before is we'll be working both with R and Python. And that's something that I want to show you here real quick, how it works, because I think Python is really powerful when it comes to working with the transformers. But R, like kind of nothing beats R when it comes to visualization. So what we're doing here is we're calling the chunk. We have the R part in here that you see here, and we're importing the df cleaned, which is the data frame that was cleaned before. We're importing it, we're assigning it to dfr cleaned, and we see here it's the arrow that you used to know from R. And what we're doing here is, again, as above, we're calculating the confusion matrix. We define the categories, we define the color palette, and we convert the confusion matrix then into a data frame, assign the column names, and then use good old ggplot to plot the confusion matrix. And here you have it as well. On the y-axis, we have the actual, like the true categories, and on the x-axis it's the predicted categories, and we do see it's just reversed in comparison to the one in Python, but we see it's really nicely performing on the positive parts, and it's also nicely performing on the negative parts, because what you want is you always want to have this diagonal being as dark as possible, because, or usually it's a dark color, because it highlights that there are a lot of matches with the negative and negatives and the positives and positives. And then what you also see here is you see that negative statements were sometimes classified as being positive. That's the 39 here. And the same goes for positive. Some positive statements were classified as being negative. And that's what we're looking at in a second, because this is, at least for me as a data scientist, if I want to improve the model, if I want to make sure that the model is doing the job I expect it to do, what I'm most interested in. Because again, the numbers, they're a good starting point, but you need to look under the hood to really understand what the model is doing. And that's what we're doing here. We're in the second step, we're evaluating the mismatches. And what I typically do, I mean, people have different approaches here, but mine is that one. I built some kind of comparison, and that could be a simple table like that. It could be a full-blown Excel sheet if you want. If you want to share it with other people, it might make sense. So I typically have the full text. I have the sentiment, the true sentiment that we have, and I have the sentiment that was predicted. And then I check, like, is it the same? Is it a match, which is here positive, positive? Whoa, love this place. Or is it something, I found this place by accident and I couldn't be happier? I mean, like for us as human beings, that's clearly positive. For the model, this sentence here is negative. And I want to see these cases. I want to see whether there's a pattern, if we can, and that probably also goes back to the rare cases question that we had earlier. I want to know if there's a pattern among those cases and where we can improve the model by either like fine-tuning the model, giving more training data, doing those things. And that's what we're doing now. Unless there are any questions, again, feel free to put them in the chat. So what we're doing is rerun a quick line of code. And what the line of code is doing, it defines whether there's a match. And it defines if there's a match. If those two columns are the same, it's a match, is yes. If they are not the same, it's no match. Then it's a no. And you'll see that in a second. We have tons of matches here, at least from what we can see here. And I think Jupyter Notebook has a really nice feature. Yeah, so it has this one where you can view even like larger parts of the table. So for instance, we have this case here. I tried the Cape Cod ravioli, probably chicken with cranberry. And the true sentiment was positive, but the model said negative. And then it becomes no match. And we'll look at those cases in more detail in a second, but that's what I typically do. And what you can also do is, because like, I mean, tabular data is nice, but if you're a visual person, having things visualized like this is even nicer. And what you're seeing here is we want to see how often we have matches and how often we don't have matches. It's kind of reiterating what we have already seen in the confusion matrix, but you see like lots of times we have matches in total terms and a few times we don't. So we see it's really only a small share, but we can also filter for them. And this is kind of the Python way of filtering. You have the R way in the R code chunks down here. But essentially what you're getting is here we only get those cases where we don't have any matches. So we see it's 74 cases, and we want to look at them in a bit. So that's the second step that I'm typically doing. So start with the numbers. Numbers are nice. Then go into the matches and no matches to get a better understanding of where things match and where they don't. And typically, as I said before, I'll be exporting these things as Excel tables. I mean, you can also use that one here, look at them in more detail. But it might, depending on the situation, it might make sense to really have something where you can edit and add notes to it. So this is kind of the next step. And what we're then doing, or what I'm then often doing, is something, and that's the explainable AI part, or which really dives into the explainable AI part. I evaluate specific cases, and I do that like depending on the model and depending on the data. You may know SHAP values and Lime, for instance. But for text data, what is most often used is integrated gradients. And that's what we're using today. And I want to give you first a bit of an intuition what integrated gradients are, and then show you how it works for text data, because that's really a cool thing. If you remember back from the introduction of the talk, in the very beginning, I said like these models are often considered black box models because so many things happen under the hood and no one really knows what's going on. And this approach here really helps us to better understand what is going on. And why are things being detected at the way they are? So why was this chicken ravioli negative? Well, it was positive. To better understand these things, we'll dive into that with the integrated gradients. So first of all, the intuition. I took this example from TensorFlow, and you can also go to the page and the link in there. So what we have here, we have the original image. And what you see is a bit pixeled. Sorry for that. But what you see, it's a water boat. So the water boat has fountains, and we want to know why this picture was classified as being water boat instead of something like a fountain or something like that. So what affected the classification here? And with the integrated gradients in an image, you would get something like that, what you see on the right-hand side. It's the attribution mask. Basically, the attribution mask tells you which components were driving the classification. And what you see here is, it's clearly the fountains, not really the boat itself, but the fountains, this kind of water that was going on there that classified the boat as being a water boat. And to get there are two steps. The first step is go for a baseline image. And for images, it really is simple to think of. It's typically like something really neutral. And here they picked a black baseline image. And then they were changing pixels one at a time and identifying which kind of pixel was driving the classification. And that's what you end up here with the attribution mask, to really understand that these here, those that are colored, are the ones that were driving the classification as being a water boat, not a color boat. And the reason why I'm going with the image here is because I think it's more intuitive to think of things as an image. But you can apply the very same logic to text data as well. And this is what we're doing here. Again, we have the sentence, Mannheim is a beautiful city. It's converted into the vectorization or the token. Then it's converted into the vector representation, the numbers. And everyone who remembers that I said before that the numbers are really important will know now why they are important. Because what we're doing is, because the model is thinking of words as numbers, not words, we can set the baseline that shouldn't have any effect on the model classification. And the baseline is often set as a 0 here, and that's why the numbers are so important. So we're setting zeros, then we're changing, within the sequence of zeros, we're changing the tokens or the single zeros. We're changing them one step at a time, and that's something that you call linear interpolation. So you're moving along the line, changing the numbers along the line. You have these two steps are just examples. There are more of them. You're changing them until you get to the 3,376. And you evaluate what's the effect of this specific number on the classification. There's a lot of heavy lifting in the background, right? So again, the algorithm here calculates the model prediction at each step and compares it to the baseline. The difference in the model's prediction at each step is then, it's mathematically done, multiplied by the corresponding step size. And then in the last step, you get the summaries, you get the integrated gradients by summing up for each input feature the results from this classification. And you get to know which input feature, meaning which word, was driving the model classification and to which extent. It's a lot of heavy lifting that goes on in the back, but I think, I don't think, I know it's really powerful. And it's a really cool way of looking at your model and better understanding what your model is doing. So this was the theory part, and we'll dive into what it's actually doing, or what it actually looks like once you apply it in your notebook. So we're going back here to the notebook, and that's something that I'm not aware that it works in R. I mean, for the transformer part, you could have done that using the torch transformers package probably. But for this one, we're using the Captain framework. It's the one up here. And it's specifically for PyTorch-based models. And we're using the library, it's called Transformers Interpret, which kind of wraps around the Captain framework and makes it nicely accessible. And I'm not aware that this already exists in R. So here you would need to revert to, or you would need to go to Python to work with that. So what we're doing is we called the library in the very beginning. And what we're doing is we're taking the sequence classification explainer method and initiate the CLS explainer. So what we like, that's just the initiation start that you're doing, similar to calling the model in the beginning and calling the tokenizer in the beginning. And what we're doing is we'll be looking at two cases. And I picked them for you because I thought they are really nice and comparable cases, or nice cases to look at. The first one is the lighting is just dark enough to set the mood, which, I mean, like reading that now as a human, I think it's positive. Or it could be also negative. I mean, it kind of depends, like, what do you think? And then the next one is, I found this place by accident and couldn't be happier. There are a couple of words that could be positive in like putting things in the context, but when you look at the single words like accident and could not, it could be also negative. And what we're doing in the next step, we'll quickly look at what the actual sentiment was for both of them and what the model predicted. So what we're seeing is actually both were positive, but they were classified as being negative. And we want to understand what is going on here and why this is happening. And we're doing this by applying the CLS explainer, the thing that we initiated or initialized up here. We're applying that to the second sentence. We can also do it to the first one, but for the moment, we're only going for the second one. So I found this place by accident and couldn't be happier. We're applying that, and we get the word attributions, meaning like how much each word, each token affects the classification. We're getting that back. And it was really fast, thinking about all the heavy lifting that happens in the back. I mean, it's nice to see when things go so fast. And what you get is you can first get the predicted class name. You can access that one here, but you can also, and that's the beauty here, you can also visualize which effect was, or how each word affected each part. And it's a bit of counterintuitive interpretation here, but what we're having here is, so the words here by accident and not, it has a strong effect on the sentiment or on the sentence being negative. So we see that by accident and not is clearly driving this sentence here as being classified as being negative. We can also, and this is something that I really like doing, because here, I mean, not only thinking about sentiments, but also thinking about, for instance, the thing with the example that I brought up earlier with the translation, to really see what is driving the translation, or for being a nurse being associated with a female person and a doctor being associated with a male person. It really, really is helpful if you think of it in a broader setting, and how you can also possibly, I mean, like for some cases, you probably won't get the right result. It might happen. But if you see clear patterns that are there and you can't explain them, this approach here really, really helps to make sense of your findings and of your sentences and of the model classifications in the end. You can, of course, also, like if you just print the word attributions and get them, you see them with numbers, because behind all these colors, there are numbers, and the higher the number, the dark, like the greener the color here becomes. And I mean, it's nice to look at it one sentence at a time, but to be honest, usually you have more than one. And what I'm showing you here is how you iterate over multiple sentences and then get the feedback for each of these sentences. And it runs relatively quick, and you get all the feedback here. And you see here, for instance, we have a sentence: I've never had such bland food, which surprised me considering the article we read focused on blah, 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 blah. And it was classified as being positive, while have never and bland were clearly driving the classification towards a more negative side here. So this is really nice to really, I think, to unpack what the model is doing. So let's go back. To sum it up and go back here, if you really want to understand your model, like 3 important things to do, in my opinion, are A, of course, look at the standard model metrics to have something how you can compare your model, but don't stop there. Start evaluating mismatches to better understand also the quality, for instance, of your data that you're having, of your labeled data. And then also go into the specific cases and unpack what is actually really happening there. And with that, I think we are approaching the end of the presentation and the workshop. Again, I've put on a few more resources here for you to look at. Again, there's also the blog post. It covers like this whole explainable AI part even in more detail, and gives you also other approaches like Lime, SHAP, and more global approaches also. Global meaning like the overall model, not specific single cases. Yeah, and with that, I would like to thank you all for joining and for walking together with me through the notebook. You still have it also after the session is over. Here's the link. Also, feel free to reach out if you have any questions. I'm always happy to chat about these things.
Okay. Oh, awesome. It's a lot of coding there, but we're really grateful. We have the recordings already, so we have the resources that we can always fall back on. And I'm really grateful to everyone that joined today. Thank you so much. We're really grateful for the interactive session that we had, for your questions, for your patience and understanding. Thank you, everybody. Thank you so much. So I want to do the final gratitude, join it to Cosima for joining us today. We're really grateful. Well, I'm really grateful for you showing up for the program, and I know your busy schedule, but we're really grateful. Thank you so much for sharing with us. Thank you so much. So I think this is going to be where we'll draw the curtain. We're going to have the recordings on YouTube, hopefully before Monday. Hopefully, I should be able to do some little tweaking there. So because of background noise and whatever we have to take to make you have a good experience watching the recordings later. And the resources are also going to be shared as well. We'll have everything up by next week. Let me just say that. So because we all have work, and we're doing a great job volunteering for this course. So thank you, everybody. We're grateful. Thank you so much. Thank you. So, Cosima, we look forward to catching up later. Thank you so much. Thank you.
Awesome. Thank you so much for having me. And thanks everyone for joining. And again, it was always, I mean, it's always a pleasure talking to such a nice and lovely crowd on this and on the topic. I really appreciated it. I put down a couple of links in the chat. Again, Bidikizo, if you want more links, let me know. And I'm happy to share them with you also for you to share them with the audience. But they are also all in the GitHub repo. So they should be accessible. And if not, if you're looking for something also, again, feel free to reach out. Happy to share things also later.
Okay. Okay. Thank you so much. We're really grateful for your generosity. Thank you very much. Thank you. So
Thank you.
looking forward to catching up with you guys later again. So thank you very much. We're grateful. Thank you so much. Thank you. So bye-bye here.
Bye-bye.
Bye.